Yes, thank you very much. I hope you can all hear me. First of all, of course, I want to thank the organizers for inviting me here. It's a pleasure that we can do these things again. It's great to see everyone. And I'm actually particularly excited to be able to talk on in this conference because I think there's lots of overlap, and I'm excited to hear what you all think about this stuff. In fact, there's some. So Fabian gave a very nice talk this morning, and you will see some recurring themes here. So yeah, there are some relations, which is of course great for me to be speaking here then. Okay, so the title of the talk is Superpotentials from Singular Divisors. So as you can imagine, this talk is going to be about computing superpotentials. And it's going to happen in a relatively, at least naively, very well understood realm, namely type 2B orientifolds, where the relevant instantons that give rise to superpotentials come from Euclidean D-branes wrapped on divisors. Maybe I should take this one, actually. Okay. And but here, there's going to be an important complication here, which arises from singular divisors, and this talk is about dealing with those. All right, so let me give you an outline, or let me actually summarize some key takeaways, which I think I can do in almost no time. So one of the things I want to explain to you is that if you dial up H01 in Calabi-Yau threefolds, you will find that 4 cycles in such Calabi-Yau threefolds are generically singular, and these are not just the sort of simple singularities at complex codimension 2, but these are happen at complex codimension 1. So then once that happens, a natural question to ask is, do the usual results about counting fermion zero modes and instantons wrapped on these divisors apply or not? And well, the answer is no. So one has to actually do some work to understand how the zero mode counting goes. So that's what I'm going to do next. I'm going to show you how to compute zero modes on such singular divisors. And then this will be a certain generalization of Witten's famous result. And then I want to, of course, apply this technology to an example where it is actually relevant, so where there are many singular divisors that contribute to the superpotential. And so I'm just going to show you the one example, but there are many more. And I find these examples very interesting because they feature, in fact, infinitely many contributions to the four-dimensional superpotential, and from a tower of 4 cycles, effective divisors. And it turns out that in these examples there are finitely many smooth divisors that contribute and infinitely many singular ones. So it's in order to understand what's the global structure of the superpotential, you do have to understand what happens with these singular divisors. And as a nice bonus, it then turns out that one can sum up these superpotentials into Jacobi theta functions. All right, here is an outline of what I'll tell you. Of course, I will start with a quick motivation and just set up conventions. And then I want to explain to you why it is true that divisor singularities become very generic, especially at large H11. And this crucially has to do with the genericity of flops that Fabian talked about earlier. So I will explain the relation between the two. And then I will go on and actually count zero modes. So generalizing Witten's result for these singular divisors. And then finally, I want to walk you through an explicit example and show you how one finds a modular superpotential there. Okay. So the sort of key motivation, at least for me, is that instantons play a key role in string model building, and there are many reasons why that is so. I guess everyone has their own take, but for me, it's especially relevant because because Axions are a key feature in the string landscape. So in fact, they appear relatively ubiquitously, which is called the string Axiverse. And what does it have to do with instantons? Well, Axions have a gauged shift symmetry phi goes to phi plus 1. At the perturbative level, it's even a continuous global symmetry. And they naturally couple to instantons via the standard action, which has a real part, which is a large number, S sub e here at weak coupling. And then the imaginary part is the coupling to the axion field. And through such a coupling, the instantons can generate periodic axion potentials in the four-dimensional effective field theory. So they will be proportional to some UV scale to the fourth power. They will be exponentially suppressed in the instanton action, and then they have the familiar cosine structure. So if you want to know about axion spectra in string theory, and especially compute them, you have to know how to compute instanton effects. And I should say, as an aside, that in addition to these effects that generate potentials for axions, there's also another well-known effect, which is called axion monotomy, which you can understand as a spontaneous breaking of the gauged discrete shift symmetry. But I'm not going to talk about that today. Okay. So what's the setup? I'm going to talk about n equals to 1, 40 n equals to 1 solutions that arise from compactifying type 2B string theory on Calabi-Yau orentifolds. And in this scenario, it's well known that the orentifold weighted Hodge numbers H1 minus and H1 plus do count a subset of the axions you get from the 10-dimensional p-forms C0, B2, C2, and C4. In particular, if you ask what are the Clusor-Klein zero modes, you can expand those of C2 and B2 into some complex torus-valued axions G, and the relevant forms are the orentifold odd 2 forms. And for C4, one can likewise do this expansion and in orentifold even 4 forms, and gets the axions phi I. I'm calling phi I here. And one can ask what happens with what's the potential for these kinds of fields in 4 dimensions separately. For instance, those from C2 and P2 are interesting in their own right, and their superpotentials can be generated from 5 planes, warped throws, geometric transitions, sorry, we've studied that in the past, but today I'm going to focus on the zero modes that come from C4. And as you probably all know, the potential for the C4 axions is generated by Euclidean D-branes wrapped on 4 cycles. So the real part of the instanton action is proportional to the Einstein frame volume of the 4 cycle, and the imaginary part comes from integrating C4 over the respective cycle, and that's how you get the coupling to the axions. So that's very easy. And on top of that, if the 4 cycle wrapped by the D3 brane is effective, it's given by a holomorphic defining equation locally, then the T3 instantons can generate one-half BPS and generate superpotential-like interactions that you can write by integrating over half of superspace, but not all of it. So that's a whole set of interactions, but the perhaps most important ones, the most interesting ones, arise when the D3 instanton only has the universal zero modes that come from breaking half the supersymmetries, because in this case you get an actual superpotential term, and that's of course very important for the vacuum structure. In our case, it determines the axion potentials. Okay, so how does that work, at least in simple cases? Well, Witten explained to us long ago how to do this, assuming that the divisors in question are smooth. In this case, the dimensions of the cohomology groups of the structure sheaf that I'm going to denote H bullet, D of O sub D, count pairs of zero modes. So in principle, one might think we already know what the answer is. So from this, it follows that in particular, if you have a smooth orentifold invariant and rigid divisor, which means that the oriented even H bullet is just 1, 0, 0, and the odd one just vanishes. Then you will get a contribution to the four-dimensional superpotential of this form. So there's a in general complicated one-loop Pfaffian in front that depends on complex structure moduli denoted Z and the axial dilatation tau. And then there's the explicit exponential, whose real part is just the volume, and the imaginary part is the axial independence. So the key question here is whether or not there's something to add to this. Namely, what if we relax the assumption that the divisors in question are smooth? Does it just still apply or not? And the answer turns out to be no. So if you just compute naively these dimensions here, you'll just get the wrong answer. So what I want to do now is explain to you, first of all, why divisor singularities are how they can arise, what the local structure of these singularities is, and what all of that has to do with flops. Okay, so as far as genericity goes, the appearance of these singularities will have to do is sort of in one-to-one correspondence with the genericity of flops in calibrated threefolds, and this has been the latter has been studied in various contexts in the Kreuzer-Skarke database of hypersurfaces in toric fourfolds and in CCs as well. And I guess I can be brief about what a flop is because Fabian already explained this to you. Namely, at least a simple flop is a topological transition between two birationally equivalent Calabi-Yau's I'm going to call X and X prime, and such that there is an isomorphism between the two once you remove a set of P1s on each side. In this case, the calacones, K sub X, K sub X prime, of these two threefolds can be thought of as being bunched together, so they share a facet along which some of these, the minimal set of P1s that you need to define this isomorphism here shrink, but then are otherwise disjoint. So here I'm drawing two-dimensional cross-sections of calacones, X and X prime, and they share this flop wall here, and you can continue past this wall in Kähler moduli space to go from X to X prime. Now, flops in general are an interesting subject, and they have been classified in the past by Katz and Morrison in this nice paper. But for today, so they're classified by something that's called a length, and maybe Andres is going to talk about this later this week. I'm not sure. This might be misinformation. When I looked at the schedule, it was still TBA, so we'll see. But for this talk, we only need the simplest type of flop, which arises from the conifold, as I will show you right now. Okay, so what is the simplest flop? It arises when you have a set of shrinking P1s, and the normal bundle of the shrinking P1 is isomorphic to O-1 plus O-1. And how does this arise? Locally, you can think about this as arising from the two inequivalent resolutions of the conifold. And for a long time, I always thought, in my ignorance, that conifolds started with Candelas and De La Osa, but of course, mathematicians knew about such flop transitions much earlier, and there's a paper by Attia about this stuff. Okay, but how does this work? So I'm going to denote X singular is the singular conifold defined by this famous defining equation here as a codimension 1 hypersurface in C4. So we have X, Y, U, V, and it's determined. You make a matrix out of it, and ask that the determinant vanishes. This is singular at the origin, so at X equal U equal V equal Y equal 0. And then you can resolve the singularity at the origin in two different ways. You can introduce projective P1 coordinates alpha and beta, and ask instead that this matrix you've made out of the four coordinates of C4 annihilates this vector of projective coordinates. And you can do this in two ways. You either do it like this, or you introduce a different set of P1 coordinates, and you instead take the transpose matrix here. So, and then there's a blowdown map going from here to here and from here to here, so they're related. and you can pass from one to the other. Okay. So what does all of this have to do with divisor singularities? That's what I want to explain to you now. And for this, first, to set up the problem in a simple way, let's consider a divisor D that intersects the exceptional P1 of a resolved cornifold transversely. And so locally, we can always just think about this as setting one of the two projective coordinates to 0 and intersecting with the remaining constraints. And if you set alpha equal to 0, we can go back here. What this means is that u and y also have to be set to 0. And you can ask, how does such a divisor continue to the next phase? Well, if we set u and y equal to 0 here, we still have this constraint here. So what we get is u equal to y equal to 0, but also we have this further constraint on coordinates x and v, which are paired with the projective p1 coordinates. And this, of course, this is just a blowup of C. That just describes a blowup of C2 at the origin. So you introduce a -1 curve. So the transformed divisor D prime here will contain the exceptional P1 of the other phase, of the other resolved cornifold, as a -1 curve at the origin, sort of. And accordingly, the intersection product will also transform. So you start with something that has, due to the transverse intersection in a singular point, it has an intersection product +1, and on the other side it will become -1, which is consistent with the usual identification of the Mori-cones on the two sides, which is basically to say that a curve class C ceases to be effective, and -C becomes effective. And these are the two P1s here. Okay, so far nothing singular. We've just described how a divisor transforms. Locally, you have a sheet of C2, and once you go through the transition, you get the origin gets blown up. It's still a smooth divisor. But now we're going to consider something slightly more complicated. Namely, we're going to assume that our divisor D intersects the exceptional P1 k times, and k bigger than 1. So again, you can write this as a constraint in the projective P1 coordinates. Namely, you just have a degree k homogeneous polynomial in those coordinates, and again, you intersect with the rest of the equations. Now, in this case, I mean, this is effectively a polynomial in just one coordinate. So near the P1, this is just equivalent to considering k disjoint sheets that all have k equal to 1. There's no difference. You can just think about this as as sheets that locally look like C2 intersecting the P1 transversely. And globally, they may or may not connect. Now, but we already discussed what happens for each individual sheet. We learned that an individual sheet gets blown up at the origin, and that the blow-up P1 that sits at the origin on the divisor is the exceptional P1 on the other side of the flop transition. So what does this mean? It means we have these k sheets all get blown up at the origin, but the P1 that's the -1 curve in each of the sheets is identified. So they all share the same P1. So in other words, all of them intersect each other along this common P1. So what does this mean? Or how, I mean, I just told you what it means, but like, what's a good name for this? I mean, you can think about this as all these sheets coming together in the common P1. So this is how a kid would draw a star. So we call this a star crossing singularity. Let me note that for the special case of k equal to 2, it's called this is a well-known thing. It's a normal crossing singularity, but here it's a little bit more complicated. So the upshot of this discussion is that flops induce divisor singularities, and that we've just proven by a local description. Okay. Now, in order to convince you that this is something that one needs to consider, one notes that flops are extremely generic. And I told you this has been studied in various ways, but let me just give you a pictorial argument for why this is true at large H11. So let me give you a picture here. This is a 2D cross-section through the extended Kähler cone of the Calabi-Yau that arises in the Kreuzer-Skake database with the largest known value of the hot number H11, which is 491. So this was made by Andres Rios-Tascon, and you can see here this very, very interesting and complicated phase diagram. So where each blob here represents one Keller cone, and this is the extended Keller cone. So all these cones are bunched together. So from the previous discussion, we see that. Does this work? Okay. We see that whenever we have a curve that is that can be flopped, then if the intersection product is less than -2, we can always go back and undo a singularity of the star crossing type. So there's a smoothness constraint, which is conversely that d times c must be greater than -1, greater or equal than -1 for all the flop curves c that one has. So generically, if you're sitting in some phase in the interior here, you're going to be surrounded by generically all flop walls. And then you can ask what divisor has non-negative or at least at most a -1 intersection with all the curves that make up the generators of the Mori cone. And the intuitive result is that this is the space of closed two forms. So to each point, so when you can pick, you can view this as moduli space, but you can also view this as the space in which divisors take values in. And so if you are in some phase, let's say this one here, well, you will find generically that the only divisors that do not suffer from these singularities are the ones that also sit inside the same small blob here. So that's exponentially small at large h1, and all other divisors will generically be singular. So this statement is very much consistent with what's known about smooth divisors, because this constraint here in particular includes the Keller cone itself, which is the ample cone. So those divisors are known to be smooth indeed, but they just make up a very, very small fraction of the allowed divisors. Okay. So this is why divisor singularities are generic. And before I go on, I want to stress something that we've learned from the local description of these singularities in terms of conifolds and different branches meeting each other in P1s. So I just went from D to D prime, making it singular, but I can also go back, of course, and I can do this via a flop transition. And now you can think about this flop transition as locally as something very simple. So you have these different sheets, and I told you that what happens across the flop transition is that each sheet has a -1 curve in it. It gets shrunk, and all the sheets get separated. So you can also just first consider what's called the normalization. So you just take these k branches here, so they meet here like a star, and you can just separate them from each other, and that's what's called a normalization. And in the second step, you blow down the -1 curves in each of the sheets. Now I'm going to define d bar as the normalization of d. So this is exactly this prescription here, and I'm going to define Hegel bullet. So this is the rune Hegel that also has the sound h, and conveniently looks like a star. So that's why we're using it. And I'm going to define it as the dimensions of the structure sheaf cohomologies of the normalization d bar. I'm sorry, there should be a bar over here as well. So that's a natural definition you can make, and we have just shown by our local description that this object here is actually an invariant under taking flops. So naturally, this will play a role now. So I'm going to start talking about the counting of Fermat zero modes on singular divisors now. Are there questions so far? Okay. So the question that I started with was how do we adapt witness result to divisors that carry such star-crossing singularities? I mean, this is a somewhat more precise version of the question I started with. Now we understand what kind of singularities to deal with. And you can guess from the last slide that our proposal is going to be to replace the ordinary H bullet by Hegel bullet, i.e. H bullet of the normalization. And I'm going to give you two independent arguments for why we think this is true. Whether or not you consider them proof, I will leave to you. But here's the first argument. Now, if you have branes intersecting along a P1, then locally it doesn't. So globally, these are going to connect to each other. It's going to be these are going to be irreducible divisors. But locally, we can just zoom in and we just see a transverse intersection between branes. So that's how we can think about this. And if we take the normalization, what this means is simply that we neglect the localized degrees of freedom that may or may not be there from open strings stretching between sheets. And this is, of course, something we usually do. Like when we consider perturbative string theory and intersecting brane models, we first ask what are the zero modes that arise from one stack, and then we arrive from open strings ending on the same stack, starting and ending on the same stack, and then what happens with the other one in the same way, and then we add whatever localized degrees of freedom come from the intersection. So now a crucial point is that the intersection curve is a P1. So we know that the open strings that stretch from one brane to the other do not actually contribute zero modes. So the dimensions, the sections of the positive and negative chirality spinor bundles are just trivial on a P1. So you just don't get any zero modes. So nothing is lost if we neglect the localized degrees of freedom from open strings stretching from one to the other stack. So in other words, if we take the normalization, we expect just from this local picture that should give the right answer. Okay, that's one argument. Now comes the second one. We consider ED3 branes wrapped on effective divisors, and they contribute to holomorphic couplings in the effective theory. And these are addressed by these holomorphic factors, e to the minus 2 pi t. So t are, roughly speaking, the complex, the Kähler moduli, which take this form here. And now, a defining feature of a flop transition is that an effective curve shrinks, but no divisor shrinks. There exist transitions where also divisor shrinks, where also divisors shrink, but this is not what I'm talking about. So here, as far as four-cycle volumes are concerned, everything stays at large volume. In particular, I can take a wall, a facet of a Kähler cone where such a flop occurs, and I can dial up the overall volume indefinitely along such a facet, and by doing so, I can dial up the instanton actions arbitrarily far. And so, we prove by this that along such loci, the superpotential expansion cannot possibly break down. All the effects that are there can be arbitrarily suppressed. So as you cross such a wall from one side to the other, it's just not possible, or at least inconceivable, that to me that a term that is present in the superpotential expansion simply disappears. In other words, if a given divisor does contribute to some holomorphic coupling, evaluated in some arbitrary phase, then it should actually contribute in all phases. In other words, the zero mode counting on BPS instantons should be invariant under flops. Now, I've already shown you before that the thing we've defined here is a flop invariant, and it coincides with a known result for the special case when the divisor is smooth. So that's the second argument. And now I'm going to use this. So I'm going to walk you through an example and construct a modular superpotential that arises from such singular divisors, applying the result I just showed you. Okay, so what's the example? We're going to take an example from the Kreuzer-Skacke database. So this means we take a Calabi-Yau hypersurface X defined by the vanishing of an anticanonical polynomial in some toric fourfold. The toric fourfold turns out to be a P1 times P1 fibration over the base P112, defined by these scaling weights here. So you see the base 112 here. You see a P1, another P1, and this means the 2 minus 1s just mean that the fibration is non-trivial. And then we can ask, okay, well, what about the obvious divisors in this case? There's D4, which you can view as setting to 0 this coordinate here. And there's D5 corresponding to setting this coordinate to 0. And you can show that they are smooth and they are rigid. They're also with a suitable orentifold. Sorry, I haven't mentioned the orentifold. We're going to orentifold by flipping the sign of the first coordinate. So there will be an O7 plane sitting on this divisor here. And once you do that, you find that D4 and D5 are in fact Orendifeld invariant, and they're rigid, they're smooth, Witten's theorem applies, and so you get at least these two contributions to the superpotential. That, of course, doesn't depend on anything I've told you before. But of course, I want to ask, what about other contributions? And the reason I'm starting with these two is that it'll turn out that you can use them as a seed and use the action of a monotomy group to get the entire set of contributing divisors. And so that I want to explain now, and in order to explain that, I will walk you through the phase diagram at the extended Kähler cone of this particular model. And it's pretty interesting. It's not yet interesting because I haven't built up the slide completely. Here I'm just showing you the two-dimensional slice through the 3D Kähler cone of this particular example. It's a simplicial Kähler cone. It's very simple. It has 3 walls. And now we can go and show that all of these 3 walls correspond to flop transitions. So what's the first one? Let's go to this one here. We pass this wall here, and we encounter a different geometrical phase. And so this is the Kähler cone of our new phase. And there's lots of interesting stuff about these phases, because it turns out that you can't actually view these as hypersurfaces in toric fourfolds that I know of. So one can use methods to just construct what the Kähler cone is here. I'm going to just sweep that under the rug for now. You can ask me if you're interested later. But what's important here is that the volumes of the divisors D4 and D5 that I showed you before shrink here. 2 points. So we get new faces of we unravel 2 faces, facets in fact, of the extended Kähler cone, because that's where divisors shrink. And now if we can go on, we can do this with either of these 2 sides. There's actually a Z2 symmetry going from left right, so it's enough to talk about one of them. And it turns out that similarly to what Fabian told you this morning, flopping from here to there, one produces a new phase that is actually isomorphic to the old phase. And the isomorphism is non-trivial, which is sort of reflected in the fact that the shape of this thing here looks different than this one here. You need a non-trivial basis change to make it manifest. So you compute the flopped Trimble intersection numbers, the flopped second Chern class, you change bases, and you see that they become the same again. And then then by Wall's theorem, you conclude that they are isomorphic phases. So you can do this on both sides here, and you get these new phases. And of course, since the phases are isomorphic, I can play the same game again. I can add copies of this one here. That's what I'm doing here. So now we have this, which is isomorphic to this, which is isomorphic to this. And along these walls, you can again ask what divisors shrink. Here it's still D4, here it's still D5, and here you get something new. I'll tell you what it is in a moment. And of course, once you've done that, you can still go here and just repeat the process infinitely many times. So what you get looks like this. There's an interesting accumulation point here. So that's what it is. And then the question is, of course, what about all these divisors? What are the classes, and do they contribute to the superpotential? So this by itself, I find an interesting example, because you find an extended Kähler cone that has infinitely many generators, and it'll turn out the effective cone of divisors will also have infinitely many generators. So how do you get them? First of all, I want to mention how one gets to non-trivial monotomies in this case, even at weak coupling. We can of course, since there's only 2 non-equivalent phases, namely this one here and this one here, we can view this part here as a fundamental domain in Kähler modular space, and we can walk from here to here. We can still walk from here to here, but the points are identified. So even though I'm drawing this as this is not drawn as a circle, these points get identified here. So actually, this means walking in a circle around some singularity. And that's of course what an element of the monotomy group should do. When you go from here to here, the basis that you need to prove that the two phases are the same, it's non-trivial, so the monotomy transformation acting on the curve in divisor lattices is also non-trivial. The spectrum moves around, and you can do this, of course, arbitrarily many times, and you sort of surround this accumulation point here. So, of course, you can use that monotomy group acting on divisor classes to generate for you the images of our divisors D4 and D5, which we already know contribute to the superpotential, to generate infinitely many more contributions. So you can just, it's a very simple exercise to work out what the monotomy group is. It's generated by this matrix here and arbitrarily many powers of it. And you can show that the gamma orbit that goes through D4 or D5, they're the same, will give you all divisors that can shrink at the boundary of the extended Kähler cone. So these are then the divisor classes that where I wrote lots of question marks here, and you can just generate them all. Thanks. So in particular, one can show that the cone of the cone of effective divisors is actually just equal to the real cone over these infinitely many divisors. Now, a key feature here is that almost all of the generators of this cone will have these star-crossing singularities, and which you can show by just figuring out what are the curves that shrink across each flop transition. You can just compute what their intersection products are, and you see that you generate these, just from a local analysis, you generate star-crossing singularities, and the number is even unbounded. So as you go towards this accumulation point here, you move all the way over here, you produce infinitely many divisors, and the further you move towards this point here, the more singularities you generate. It never stops. Okay, so by the same token, the normalization of each of these divisors that sit in this generating set here is isomorphic to, say, the divisor D4, modulo blowdowns of -1 curves. So this is true for all these generators, and in particular, the sort of stringy Hodge vector, the one that actually that counts the physical zero modes, is 1,0,0 for all the generators, and all of them contribute. So it follows from this analysis that the superpotential takes this form. We can write it as a sum over the elements of this group. We have some prefactors again that are the one-loop Pfaffians, generically dependent on z and tau, and we have the explicit e to the minus volume factors. Now, in general, these things are hard to compute. Though I should refer to Sergei's talk on, I think, Thursday, who's I think going to talk about some exciting developments there. But we won't actually need the structure of these Pfaffians explicitly, because we know that all contributing divisors are related by a symmetry transformation coming from the monotomy group. So we can just pull out this one overall factor outside. It doesn't depend on gamma. And this means we can actually compute we can completely compute what the Kähler modular dependence of the non-perturbative superpotential is. We can just do the sum here. We can present it in a basis. When it takes this form, there's 3 Kähler moduli T1, T2, T3, and there's some prefactors. And now we can do the sum, and you realize that this defines a Jacobi theta function. Modulo some exponential prefactors. And I should note that that superpotentials of a form like this have been observed in other contexts in the literature, but this context is very different, and the way the superpotential arises is technically very different as well. Now, if I use the result that I believe Sergei is going to talk about, then which is the absence of multi-covering corrections to the superpotential, then this implies that this expression here is actually exact. Now, what can we do with this? In general, I don't know, but there are some things that I think are worth pointing out and thinking about. Namely, of course, the superpotential being proportional to the Jacobi theta function inherits its modular properties. So in particular, there's a sort of S duality that inverts divisor volumes. So tau3 is proportional to to a Kähler modulus here. So you're going to invert the value of a Kähler modulus, and this transforms nicely under it. So of course, just because the superpotential that we've computed transforms nicely under some S duality, some S transformation, it doesn't mean that this is an exact duality of the n equals to 1 effective field theory. But I think at this point it's very tempting to speculate that this is actually true, so that these transformations will lift to exact dualities of the effective theory. Another thing you can ask is, well, do they exist supersymmetric vacua? Once you've computed a superpotential, you should ask this question, right? What are there moduli spaces? What's the vacuum structure? Well, in this case, it's a little disappointing because this superpotential, I mean, the Jacobi theta function only has simple roots. So there are no supersymmetric vacua that you can control without knowing the Kähler potential. So supersymmetric ones would be dw equal w equal to 0. So in the F-term equations, the Kähler potential will drop out. So that doesn't work in this example, but I mean, the general lessons learned here can in principle be applied to other examples that have a more complicated structure, and I see no reason why there can't be supersymmetric moduli spaces in these theories. So I think that would be very exciting to study in the future. But for now, let me just conclude and let me give you a quick summary. We have first argued that star crossing singularities are generic in Calabi-Yau threefolds, especially as you dial up the Hodge number H11. And then we dealt with these singularities. We generalized witness counting of Fermion zero modes and for wrapped Euclidean D3 branes into the regime where these singularities are present. You can show that just naively applying witness result gives you the wrong answer. We found what the right answer is, and then we use this to give examples where infinitely many such divisors contribute to the superpotential in an interesting way. Namely, you can sum everything up into a Jacobi theta function, and I think it'd be exciting to study these models more in the future. So those are the possible future directions I want to point out. Do more examples. Look at what superpotentials you get, and see if there's something you can learn about those. And of course, independently, one should try to study from a perhaps more microscopic point of view what these proposed n equals to 1 dualities are that involve the inversion of divisor volumes. I don't think it's completely implausible that one can learn something about n equals to 1 vacua at strong coupling, i.e. where Einstein frame divisor volumes are of order 1. Okay, so those are the closing remarks, and I want to just thank you for listening to this talk.
Thank you, Moritz, for this very nice talk. I think there was Naki, Kumro, and then Thomas.
Thank you for the good question. You didn't mention anything about charge mode, but did you mention
Yes, yeah. Oh, sorry. Yeah, I didn't talk about charge zero modes coming from intersections of branes with O planes and 7 branes. Indeed, and I've swept that under the rug a little bit because in this very simple example you have. So let me maybe go back. So there's an 07 plane sitting at the divisor D1, so corresponding to setting to 0 the first coordinate. So there's a 7 brane stack there, and you can ask what are the zero modes that come from ED3 branes intersecting this 7 brane locus. And indeed, there are charged zero modes. So the dissection is a torus. It's not a P1. So in this case, one can ask, well, what about these zero modes? I expect that if you Higgs the gauge group, they should be lifted. But in this case, without doing that, they're not. There's a different example that we presented in our paper just because of that, because we wanted to make sure that there's another example where this does not apply. I didn't show you this example because it's a little bit more complicated. It has H1 4, not 3. But so these sometimes occur and sometimes they don't.
There was another question.
Yes, very nice talk, Jacob. There's a follow-up to the work that Witten and Donaghy et al. Did, where they claim that there's a claim to say that they missed the 1/8 of some power denominator in their theta function. That is superpotential have a correction having to do with degenerate instantons of the contribution that they didn't include. Would there be a room for that in your context? And I think the argument there was based on the weight of the modular form it has to have. It has a wrong weight data function. So, in other words, the eta factor would calculate to give a negative weight instead of the positive weight or something. So, would there be a room for similar correction in your case?
I don't see right now how that could arise, but that's very interesting. Maybe you can tell me which paper it is, and I can look at it. Yeah, I don't see why would it apply here, but yeah, I don't.
The question I had was that if you take the case of a Calabria which is rigid, like the Z-manifold, and the orientifold, are your techniques applicable in those cases? If so, I mean, how difficult is this to compute?
Yeah, again, I don't see an obstruction. Why it wouldn't be possible? We studied these cases simply because we had them right in front of us and they gave us nice results. But yeah, you can definitely try it for rigid Calabrias.
And then there's a third question that is, if you take Calabria threefold, the orientifold you did can be embedded into FTA context and viewed as a Calabria fourfold. In this context, I believe a while back, like maybe 20 years ago, Lerfit suggested that maybe there's a connection between generating superpotentials by going to the mirror Calabria, by turning on the G-flux in the mirror language. Could it be that the superpotentials that you're computing become classical in the mirror by G-flux in the mirror?
Yeah, I think that's entirely possible. The question is how would they... So these are suppressed in Einstein frame volumes, but that's not a problem well, I would think under mirror symmetry they get mapped to ED2 instantons. At least for threefold mirror symmetry, but you're using F3 first, so I'm not sure. That's interesting. Yeah, I need to think about that.
All right, I think there was Thomas first.
Yeah, we can also discuss later.
Yeah.
Yeah, maybe let's discuss.
Okay.
I think Peter was in first.
Okay, I have maybe just a question about notation. Can you show the slide where you show the modular superpotential? I think it was the last slide. Yes, right now.
Yeah. Mm-hmm.
The Z is defined to be the difference between T2 and T1.
Uh-huh.
The Z also appears in the first function A. Is it the same?
Oh, I'm so sorry. No. Oh, that's terrible. No, this is a complex structure modulus, and this is... Yeah. Sorry about that. No, they're different.
Okay, but
The first Z is a complex structure.
Yes.
I've seen two more questions. There was one question there.
The center origin of the model symmetry.
I don't. I think it's we thought about it a little bit. We didn't. Yeah.
To understand the weight.
So like microscopically, where the weight comes from. So, yeah. I don't know. I think these are all very interesting questions. I'm sorry, I don't. Yeah, but that's true. But okay, so the monotomy symmetry. So this is of course invariant under the monotomy symmetry, but this one rises beyond. So this is a result of the of this. It doesn't. It's not. We didn't put it in. It just came out. So I'm not sure if one can. I mean, whatever one can use to understand how this comes about, it has to do with strongly coupled physics. Yeah, but would be very cool to understand that.
Right, two more questions. There was one over there.
Mm-hmm. Yes. Uh-huh. Mm-hmm. Yeah. In fact, I should have mentioned this because actually we have a nice solution to this. So I swept that on the rug. In the paper, you can find it in a series of footnotes. But so what one can show here is so you have a monotomy symmetry that's generated by just one element. So you can ask how does this act on the geometry, and you can in particular ask does it have fixed points. And you can prove there exist fixed points of this map. I don't know if so you can put the D3 branes at these fixed points, and these fixed points do not touch these ED3 branes that you can also show. And then once you have shown it for the first map, of course, you just take powers of the map and it stays the same. And so in this way, at least you can put the D3 branes at a position where modularity is not spontaneously broken. It can be spontaneously broken, which is also interesting. But yeah, there exist unbroken points. Yeah.
Okay, and
Sorry.
one last question over there.
Yeah, thank you for the nice talk. So to address that point, I think what's happening is you have a multi-section operation between one operation and multi-section. And then tau 3 is just a scale Kerr modulus associated with the generic fiber. So what you have here as the S-duality, tau 3 goes minus 1 over tau 3, due to the rescaling is just a Fricket duality, which transforms the petition function into the petition function of non-commutatively resolved things.
That sounds very interesting. Yeah, let's maybe talk about it afterwards. I want to hear more about it. I mean, here it's a 4-cycle volume, but maybe you can dualize it to view just this volume of a fiber of something. Yeah.
Okay, how many questions do we still have?
Okay.
1, 2, 3 more? 2, maybe the last 2 short questions, please.
Yeah, okay, so if I am understanding correctly, the fact that you have a modular superpotential comes from the fact that the kiloton was infinitely generated
Mhm.
for phases.
Mhm.
Do you know like how generic this is, or if you can see like a priori if there is a spectacle of the wafers after and all?
Yeah, short answer, I think it has to do with P1 times P1 factors. But so whenever they arise, so whenever you have a P1 times P1 vibration over something in the ambient variety, it seems to occur. Yeah, so there are theorems of when it cannot occur, and that evades the theorem. So yeah, okay, short. That's a short answer.
The last question.
Do you think it's possible to come up with something like the DC Witten effect, where you get destructive interference from the sun, and this becomes, you get exactly 0.
You mean for each individual term, or for the different terms in the series?
So you can, within a class, monotomy class,
Yeah.
it becomes like the sun.
So I don't think so, and the reason is that I mean the way that Beasley-Witten works for worldsheet instantons is that you have different contributions coming from different regions of the Calabi-Yau, and they have the right phases to just cancel each other. In this case, these are divisors, they're rigid divisors. There exists a single section. There exists only one representative. I don't see how at weak string coupling that could lead to a cancellation. I don't see how at weak string coupling that could lead to a cancellation, but sorry? Yeah. 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 But I mean these are then functions of the string coupling that sit out in front, right? I mean there are no B2 and C2 fields either here, so no. Mm-hmm. Mm-hmm. Right. Okay, that's very interesting. I need to think about it. I would be surprised if that leads to a cancellation, but.